Those are your notes for this one.
No, for modern history.
How do you do that?
That's a lot of it. I think the most have taken time.
What?
So much specialized.
If I don't just know, it's fine. I know, it's on there.
All right. So let's see. Laptops, like slides if I need to.
A reliable source.
All right, who wants to break the ice? Who wants to ask? Where's my chalkboard? Back there. The first question. No questions? All right, I guess we're done then. Ooh, slowly.
What's the difference between mass and weight?
What is the difference between mass and weight? So, weight is the force of gravity acting on something. So weight's a force. Whereas mass, your book defines it as a common definition, which is really kind of crap, honestly. Because mass is the quantity of matter that something contains, whatever that means. But the important point is mass refers to a body's inertia, its resistance to being accelerated. What's the big difference between mass and weight? Your mass is the same no matter where you are in the universe. If your mass is 100 kilograms on Earth, then it's 100 kilograms on the moon. It's 100 kilograms on Mars. It's 100 kilograms anywhere, whereas your weight changes. We often will give, like on metric scales, we'll say, oh, I weigh 70 kilograms or whatever. That's actually not right. Your weight is actually a number of newtons, because it's a force. And your weight depends on the strength of the gravity on whatever planet or whatever it is that you're standing. So mass doesn't change, weight does. If weight's a force, mass is not. Does that make it clear? Is that okay? Anybody want to ask anything else about that? Okay, hearing none. Is that okay? Does that work for you? Okay. Who wants to ask the next question? Yes?
Velocity versus acceleration.
Velocity versus acceleration. Yeah. So, acceleration is the time rate of change of velocity. So, velocity is what is changing when something is accelerating. And remember that velocity is a vector. So that means that even though in common everyday usage, we often use velocity and speed interchangeably, even physicists are often guilty of that. But in fact, velocity contains both how fast you're going, your speed, and what direction you're headed. And so the idea is that if there is any change in either how fast you're going or what direction you're headed, you are undergoing acceleration. So, yeah, go ahead.
If I'm running in a circle at a constant speed, is that acceleration as well?
That is an example of acceleration because my velocity is changing. My speed is not changing, but the direction I'm moving is changing as I go around the circle. So if I'm going around the circle at a constant speed, or even if I'm not going around if I'm going around the circle at a not constant speed, either way, I am accelerating. Any change in how fast you're going and or the direction you're headed in is accelerated motion, is acceleration, and it requires a net force in order to produce it.
So if I'm driving in a car at cruise control on a straight highway, there's no acceleration.
There is no acceleration. If you're driving in cruise control on a straight highway, there's no acceleration. And in fact, it's kind of useful to think of it like this. You have, in a car, we usually think if there's one pedal that we call the accelerator, but from a physics perspective, you have three things in your car, all of which are accelerators in that they cause acceleration. There is the gas pedal, what we normally call the accelerator. The brake pedal changes your speed, so that's also an accelerator from that standpoint of view. What's the third thing in your car that can accelerate you? Yeah, the steering wheel changes your direction of motion, so all three of those things cause the car to accelerate. But if you're in cruise control on a straight road, then you are not accelerating in that case. But that's the only case, pretty much. The only way not to be accelerating is moving in a straight line at constant speed. Anything else, and you're accelerating. Yes?
Okay, so I'm looking at like the different forms of energy. Could you explain what exactly mass energy is?
Yeah, so mass energy is what shows up in Einstein's most famous formula. Probably, except maybe for F equals ma, the most famous formula in all of physics, the one that says that E equals mc squared. So mc squared, the mass times the speed of light squared, is the energy associated with a given amount of mass. Before Einstein came along and made us realize that, we didn't know that you can actually convert mass into energy and vice versa. And so, in fact, the way that the sun shines, as we will discover in glorious detail, is that when hydrogen fuses into helium inside the sun, the helium that is produced has a little bit less mass than the hydrogen that went into it. Where does that missing mass go? It's converted into energy. It's the energy by which the sun shines. That's how nuclear reactors in general work, is they're converting a little bit of mass into energy. And that's what mass energy represents, basically. It's referring to the fact that anything that has mass has the potential to be turned into energy. Is that okay? So I was saying, any follow-ups on that? Anybody want any clarification on that? Yes?
What direction does the acceleration vector point in uniform circular motion?
Yeah, so in uniform circular motion, it points towards the center. And the way you can figure that out is imagining that you picked up your little sister, or if you don't have a little sister, find a kid you know on the street. Don't pick up a random kid. You'll be in trouble. Find a kid you know who thinks it's fun to be swung around in circles. And you will discover that you need to pull inwards on the little kid in order to keep them from flying off. You're pulling inwards, you're producing a force inwards on them, and since force and acceleration, the net force and the acceleration are always in the same direction, if you're pulling inwards, if your force on them to make them move in that circle is inwards, that means their acceleration as a result of going around that circle is inwards as well. So it points towards the center, in other words. It's what we call a centripetal acceleration. Yes?
So if you let the kid go, he's going to accelerate in the direction that he was like last heading?
No, actually, if you let the kid go, there's no more force. And so, well, except for gravity. Let's do this on the International Space Station, okay, where you're just falling around the Earth. Or maybe even better yet, we'll go on a rocket voyage because NASA has spent billions of dollars to study kids going around in circles. We go to a rocket voyage far from any planets, and stars. We're out in interstellar space, so gravity's really weak out there. Swing kid around in a circle. Yep, gotta pull in. Let go of kid. No more force on kid. How do things move if there's no force on them? They move in a at straight line at constant speed, right? Newton's first law. No force, moves in a straight line at constant speed. So you let go of the kid, he moves in a straight line at constant speed, no longer accelerating. Moving in a straight line at constant speed, no force, no acceleration.
Okay.
So when you let go, no force, no acceleration. Do it on the surface of the Earth, no more horizontal force, no more horizontal acceleration. So horizontally speaking, kid flies off in a straight line at constant speed, but there's still a gravity force, so on the whole, kid goes, mommy, and all that kind of stuff, because there will be a vertical acceleration due to the vertical force of gravity in that case. Yes?
You know what the difference between thermal energy and radiative energy?
Yeah, so thermal energy is energy associated with the kinetic energies of motion of the atoms and molecules of which a substance is composed. So if I have an iron skillet, then the iron atoms are all jiggling back and forth very rapidly, literally at thousands of miles an hour. But they're not really going very far because they just keep going very microscopic motions. And the thermal energy is you add up all the kinetic energy of motion of all those jiggling molecules or atoms. That's the thermal energy. Okay. Radiative energy is energy that is not actually possessed by the body. It's energy that it's giving off into space. So in other words, you have thermal energy because you have a non-zero temperature. Your temperature is not absolute zero, which is good. If your temperature was absolute zero, well, first of all, you'd be breaking the laws of physics. You can't actually get down all the way to absolute zero. Second of all, it would suck, because you wouldn't be alive. That tends to rule your day. You've got thermal energy. At the same time, you are giving off radiative energy. We cannot see the radiative energy that we give off because it's in the infrared part of the electromagnetic spectrum. But there are cameras which are capable of recording infrared light, and if we had such a camera here, one that looks in the far infrared part of the spectrum, you would be able to see everybody literally glowing from the radiative energy that they were giving off. And if nothing is replenishing it, the radiation would be depleting your thermal energy. It would be coming at the expense of your thermal energy. So you'd be cooling down because you were giving off that radiative energy. But there is something replacing it, namely you have metabolism. So you keep burning sugars and producing energy that keeps your temperature up. So without that, you just cool down. Just like if you take a loaf of bread out of the oven, it cools down because there's nothing continuing to replenish thermal energy, and so it gives off infrared radiation, cools down without anything to replace it. Yes?
So this is like if you're cold and you stand in a group of people, you're going to be warm because that's like the heat coming off of those other people.
Yeah, if you so there's why is it nice to stand next to somebody warm? There's a couple of reasons for that. First of all, if you're just standing near them, yeah, then you'll get some infrared radiation from them that'll warm you. If you stand by a fire, you're feeling, the heat you feel is infrared radiation coming to you from the fire. If you feel the warm sun, you're feeling infrared radiation from the sun warming your skin. That's how heat lamps work. They give off infrared radiation. There's other things too, because the warm air in contact with your skin gets heated directly by air molecules colliding with skin molecules and so forth. So you can feel a warm draft from the other person from that. They can transfer energy to you that way. If you say, oh, I'm cold, hug me, your direct contact with one another can transfer energy. But you've probably noticed that if you like walk up to somebody and hold your hand near their face, you might feel a little bit of warmth there, and that's infrared radiation from their face transferring energy to your hand. Yep. We can't see ourselves glow, but we can feel ourselves glow, so to speak.
Will you give us equations for any math problems?
Yeah, I will give you the equations, and your job is to know what to do with them.
Okay.
So I won't necessarily, I would say like, Newton's form of Kepler's third law, p squared equals 4 pi squared over gm a cubed. And I would give you the value of g, the gravitation constant. I would expect you to know that p is period, time to go once around the orbit, and in that version, that should be in seconds. And I would want you to know that A is the semi-major axis, half the long axis of the elliptical orbit, and that should be in meters in that equation. And the mass is going to be in kilograms in that equation. In the deluxe Newton's third law version of Newton's version of Kepler's third law, we're using kind of laboratory units, MKS, meters, kilograms, seconds, units in that situation. Whereas if you have things orbiting the sun or another star the same mass as the sun, it's more convenient, you don't have to, but if you don't, you're a fool, it's more convenient to use p squared equals a cubed, where p is in, not seconds this time. If I'm using p squared equals a cubed because I'm going around a star the mass of the sun, it's more convenient to do that, you have to make p in, yes, years, and a in AU, because in that case we're kind of using Earth as the standard. So we express the period in terms of Earth's period, 1 year. And we express the semi-major axis in terms of Earth's semi-major axis, 1 AU. We could have used any planet to do that, but we kind of like this one, and so we use Earth as the standard. Yes?
Can you do a sample problem with that?
Why, yes, I could do a sample problem with that, yes.
Can you do like when you would use seconds and when you would use what?
Yeah, so, okay, so let's kind of lay it out here. So, we got,
Well,
e squared equals a cubed. Use this when the body being orbited is the sun or a star of the same mass. But when we use this formula, when we're orbiting the sun or a star of the same mass, remember the general formula is p squared is k times a cubed. But that constant k, most conveniently, is if you can pick units where it's equal to 1, and a choice of units where it's equal to 1 is where p is in years, a is in AU. So, if the body being orbited is the sun or a star having the same mass as the sun, generally your easiest route will be to use this version. So if you're given A in some other units, turn it into AU and then do the calculations. Now, the more general equation, Newton's form of Kepler's third law, is p squared is 4 pi squared over g times m times a cubed, and m is the sum of the masses, but if one body, and that's pretty much what we'll always have for now. When we get to double stars, no, but for now, if one body is much more massive, m is essentially if a satellite is going around Mars. Mars is way, way, way more massive than the satellite, so m is basically just the mass of Mars in that situation. And furthermore, m is in kilograms. So in the deluxe formula, so to speak, we use MKS units, meters, kilograms, seconds, units. We want to use kind of like laboratory units. And MKS, meters, kilograms, seconds. So A is in what units? Meters, because A is a distance, right? A is a distance. A is, so we've got a body of some tiny little mass, little m, going around a body of much larger mass, big M. That much larger mass is sitting at one focus of the elliptical orbit, Kepler's first law, and 1/2 of the long axis of the ellipse is what A represents, the semi-major axis, semi as in half, semi-major axis. So that's a distance. So out of meters, kilograms, seconds, A's got to be the one that's a distance. It's in meters. P is what kind of quantity? What does it represent? P is the orbital period. That is the to go once around the orbit. The time to go once around the orbit. So P is in seconds. P is the one in seconds. So when we're using this version of the formula, we want P in seconds. P is seconds. P is in seconds. P is in seconds. A is in meters. M is in kilograms. And so that's the rules as far as that's concerned. Okay, so happy with that? Yes?
So basically, if the question involves that's how you know to use the equation, if not.
Yeah, so, but careful, so you're right. If the question asks you what M is, yeah, you're going to be using this one because the only time you can use this one is if the mass is the same as the sun. So I wouldn't be asking you, what's the mass if it's automatically the same as the mass of the sun. But be careful. Don't make that make you think that you would never use this formula if you weren't asked for the mass. You could be asked, what is the orbital period of a satellite of Jupiter given that its semi-major axis is so many kilometers and the mass of Jupiter is so many kilograms, right? So there is kind of a cue in that if you're given a mass, you better use this formula. Because unless the mass you're given is it's orbiting the sun, or it's orbiting a star the same mass as the sun. If you're given a mass that isn't the mass of the sun, yep, better use that formula. Yep. Yes?
Will you give us the information like the Earth distance from Earth to the sun or whatever?
Well, remember, that's one of the things I list on the sheet that I want you to know. Is
Okay.
this, that an AU is 150 million kilometers, and that it's actually 149.6 million kilometers, but 150 million kilometers is good enough. I do want you to know that.
Okay. So like all the significant information.
Yeah, but the thing is that so if it's a number that I don't say know this on the study guide, then I will provide it for you. Like the value of the gravitation constant. I don't expect you to remember that it's 6.67 times 10 to the minus 7 in MKS units, for example. Yes?
So if I wanted to solve for A,
Yeah.
I would want to divide P squared by A cubed.
No, you don't want to do that. You
But
don't
like,
do that.
to get A by itself, basically.
Right, so let's talk about that. And eventually, just like, could we do an example problem? We'll get to that. Okay, I know, I haven't forgotten. But, okay, so, yeah, so this is written in the form where I tell you what A is and what M is, and your job is to tell me what P is, because this already says P squared equals something. But what if the question is blah, 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 what is the semi-major axis? You know, something of that form. When I say that, what thing am I asking you to find? Am I asking you to find P? Am I asking you to find M? Am I asking you to find A? I'm asking you to find A. So that means you want a formula of the form A equals. Or we could have it A cubed equals and then take the cube root when we're done. Because I've already got A cubed in this formula, so let's make it A cubed equals something. Well, notice what you're trying to do is get this stuff over there, because then you'd have A cubed by itself on the right-hand side. How can I get 4 pi squared over GM, how can I get that to the other side of the equation? You don't want to subtract it, I heard them, yeah, you flip it basically. You flip it over, that's how I mentally think of it. If you want to do it kind of, you know, fully, rigorously, what you say is, okay, if I multiply both sides of this equation by GM over 4 pi squared, that'll cancel 4 pi squared over GM. So I multiply both sides by, it's algebra time, and there's much rejoicing. Multiply both sides by GM over 4 pi squared. So that if I multiply both sides by the same thing, it stays equal. So GM over 4 pi squared times P squared is equal to GM over 4 pi squared times 4 pi squared over GM times A cubed. But if I take GM over 4 pi squared and multiply it by 4 pi squared over GM, what do I get? Not 0. Yeah, you get 1, right? Because the GMs cancel, 4 pi squareds cancel. So this turns into A cubed on one side is GM over 4 pi squared times P squared. Oh, glorious. That's what I want. Because now it says, okay, plug in everything over here. That'll tell me what A cubed is. Then take the cube root of that, and that'll give me the answer that I want. Now, do I write this out when I'm solving like this? No, what I do, and if the teacher never told you this, then why not, is mentally what you can do is just say, okay, to get a given quantity from one side of the equation to the other, just move it over there, flipped over. Because that's ultimately what happens. In other words, notice that the relationship between this equation right here and this equation right here is that I flipped over GM over 4 pi squared and took it over to the other side. And that always works. You can always take something from one side of the equation to the other by flipping it over before you move it to the other side. So mentally, that's how I do that kind of algebra. So this is what you want if you are trying to figure out what the semi-major axis is. Now, of course, you can commit that to memory, but then you're kind of doing the thing of spending an hour to save. You know, people will often spend 20 minutes memorizing something to save themselves 2 minutes of thinking about it. So my recommendation is just be able to know, because this is what I would give you, be able to know that if you want to rearrange it to that form, you just got to flip that over to the other side, as opposed to, oh man, I got to remember it's A cubed equals, oh crap, was the 4 pi squared on the top and the bottom? Okay, you know, you don't want to be in that kind of situation. So this is what we would want if we wanted to solve for A. What if I want to solve for M? If I've got B squared equals 4 pi squared over GM A cubed. What if I want to write that where it's M equals something? How can I do that? How can I get the M from this side of the equation to this side of the equation.
Multiplied by uniform squared.
Um,
Divided by p squared.
So that'll all be in there. Just to, so I'm not disagreeing with you, but so far, let's just move m by itself to the other side of the equation. What do I do? Multiply both sides by m, right? If I multiply both sides by m, multiply both sides by m, then I get mp squared is equal to 4 pi squared over g times a cubed. Notice that actually follows the rule, because think of it, over here you got 1 over m. Something in the denominator, the m denominator is 1 over m. How do I take 1 over m to the other side? I flip it over. Well, if I flip over 1 over m, that's m. So even though what I really did is I multiplied both sides by m, mentally what I did is I said, I can just take it from the bottom over there to the top over there. It always works. What's on the bottom on one side can be moved to the top on the other side. But now I want m by itself. There's this pesky p squared there. What do I do to it? I divide by p squared. Or, it's on the top over here, I can move it to the bottom over there. So, strictly speaking, divide by p squared. Mentally what I do, move it over to the other side, but put it on the bottom instead of the top. So m equals 4 pi squared over g, a cubed divided by p squared. And yeah, you could have put 4 pi squared over g p squared times a cubed. Doesn't matter. Just as long as it's on the bottom somewhere, your calculator is not going to care. It's all the same thing. So this is the form I want. If I am told what a is, and I'm told what p is, and I'm supposed to figure out what m is, that's the form that I want. Yes?
Is that the like same equation that we've been doing on our master and Charlie?
Okay. Yeah. So problem 452, the one that had 6 different, this, that, and the other thing of this moon is going around that planet with this many blippy blobs and all that. They're all applications of either this or this or this. They're all rearrangements of this single equation right there, ultimately. Yes? Yeah. Okay. So, do an example? Question mark? Do an example? Right. Okay. So, can I erase or not? Anybody gonna stop me? 3, 2, 1. Okay. Well, it's okay. I don't, like have to be doing something off. Okay. I'll make something up. The moon, I don't know, Fred orbits planet Jim